Hello, it is an exciting day because today we're going to University of Bonn departments of physics and astrophysics and so on and so on. And they have a special program for beer mat throwing. 3 of the scientists there, including one head of an institute, designed a machine to throw beer mats and at the same time to find out why they never take exactly the same direction and which forces pull them up, down and to the side. Did you ever ask yourself why that is?
No.
But you did. What do you expect, even though you never asked yourself the question?
It is random or is it not?
Is the flight path random or is it not random? And as you probably expect, this is the core, this is the center of the whole, all the calculations and the experiments. Because as you might guess, it is probably not random and not chaotic. Because we are in Germany. There's no chaos or nothing random here. We are now already in the middle of Bonn. It was the capital city of Germany for quite a while after the Second World War. You see it's pretty green. A lot of students living here. And now we are going to the Institute for Radiation and Nuclear and Radiation and Nuclear Physics. Are you excited?
Yes.
Maybe we see another Stellarator or something. I don't think so. I don't think so. We saw a fusion reactor once in Germany, in Greifswald, but I fear no fusion reactor this time, but beer mats. But that it's probably even more impressive. After many years, since the 90s, I think, 1990s, at the Ig Nobel Prize Committee, I know that even the most unlikely research may discover something that is beautiful, interesting, and may sound funny, but has some very thorough implications. So for all of you Ig Nobel fans, this way, for all of you Ig Nobel fans, I'm kind of excited. All right, here we are. This is Ines, this is Art on the lawn, and this is probably one of our hosts. Hello, host. This is Carlsen. He waited for us. That's very polite and very German.
Hi, nice to meet you.
Ines is very interested in stellarators and fusion reactors since she saw one in Greifswald. Are we to expect one here in this building?
No, unfortunately not.
No stellarator, no other fusion reactor?
No.
So what is your main type of research that you're doing here?
Well, I mean, there are different types. So the experimental groups here in the building mainly do hadron physics. Not sure whether you know what that is, but...
Very small, the particles?
Yeah, so it's really about the smallest particle that exists in nature and how they are built from the fundamental degrees of freedom. And we have actually an accelerator here in the university, which is sort of unique in the German university.
A particle accelerator?
Yeah, particle accelerator.
Which type?
It's called ELSA. It's an electron stretcher, so it's electrons that are running there.
But today we are not talking about hadron collisions, but we are talking about beer mats.
Exactly.
Do you drink beer?
Alcohol-free, yes.
Here comes the new guy, and you are not from this building. You're from another building.
No, I'm an astrophysicist, and I'm from the astrophysics building.
So you are not dealing with hadrons, but with stars, or what's that?
With stars, indeed, mostly with binary stars, so 2 stars orbiting each other.
How did you come to work with stars? Were you one of these geek kids that were looking into the stars and
Yes.
watching them? Yes.
Yes.
There you go. What happens when 3 physicists trying to switch on a machine?
Ja, genau.
Then try the others.
No power right now.
I mean, we are theorists.
You're all theorists.
We're all theorists.
You're all theorists.
Yes.
Why did you build a real machine that really does things, being theorists?
Well, because you can't do theory without really good experimental signals. I mean, where do you start if you don't have anything to compare with?
But I thought this was a big fight between theoretical and practical physicists, but that's not the case.
You mean the beer mat?
You respect each other? No, I mean in general terms.
Yeah, but this is like Cologne and Düsseldorf. It's more on the
not serious.
On the not theoretical.
Ah,
yeah.
I see. Did you know that, Ines? That practical experimental physicists and theoretical ones like each other?
No.
This is the machine now. This is, as you can see, it is a specialized machine on the one hand, but it looks robust on the other hand. And your workshop built it for you. What did you tell the guys or the girls or the workers down at the workshop?
Yeah, we first formulated the problem and that we would need a machine that reproducibly shoots the beer mats with a definite rotation speed and also with a speed in forward direction.
Is that can that be calculated? The rotation speed. I mean, is that something that you can? I don't know. Tell them in a mathematical way, or do you just try? Is it just trial and error at the end of the day for the guys at the workshop? I mean, not for you.
Well, I mean, they built in two motors, right, which independently drive these two bands here, and from the speed of these bands, we can compute the rotation and the forward speed.
That can be done on paper, I guess, with a pen and paper. It's not.
And
it's not
this
that
is the practical way how to do it.
We use this nice laser device here.
So you also measure it. You just you don't just
of
calculate it.
And with this we can measure the rotation speed.
Rotation is measured by measuring this little sticker here. Do I understand that right?
Yeah.
With the laser machine. First you wanted to build it in the machine, but that didn't actually...
No, actually that took quite a long time with the electronics workshop. Also in this house they tried to invent some mechanism that measures the rotation speed from within, but in the end they gave up and they just gave us
dirty,
this...
dirty with the laser machine. Why is it important to know exactly how many rotations the beer mat did make when it flew off the machine?
Well, if we want to know what's really happening and we have a theoretical underground developed, we need to have reproducible events. So if one beer deck flies completely different than the other, we cannot prove anything.
Especially since your question was, how do beer mats fly at all? So you need starting conditions to understand what happens afterwards,
Yes.
correct? My wife thinks that the whole beer mat flying is a chaotic process. But probably it's not, because you investigated everything and now you know everything about beer mat flying, and it's not chaotic. Is that correct?
Of course, we know everything now. Actually, in the regime we investigated with large rotational velocities, it's not chaotic. We can really perfectly predict the flight of a beer mat, and the machine also shoots them very reproducibly for a long distance. They really travel the completely similar route every time. But if you throw them without initial rotation, then it tends to be quite chaotic.
Verstehe. Okay, so first you discovered that when you're not spinning, you have to show it again, I'm sorry. When you're not spinning the beer mats, then you have two preferred landing sites for your beer mats. Is that correct?
Actually, it was the other way around. Originally, we threw with rotation, but then we also investigated what happens without rotation. And if you throw a beer mat without any rotation, then it has two possibilities. It either flies up immediately or it flies down. If it flies down, it just crashes into the floor, and this makes a nice reproducible blob. Whereas if it flies upwards, it gains height, and then it tumbles through the air and flies somewhere in a semicircle.
But not completely somewhere, in a semicircle.
Yeah.
Already interesting. Try it at home. And you said you have a physics show where you threw beer mats in a beer garden in Bavaria. Who does the physics show? You? And you too? And you too? All of you? Yes?
Yes, you
Me
and
not, I'm not.
You're the professor. He's the professor.
Well, I joined at some point making some music, but it's really a student thing, and they are doing it together with one professor, and it's not my honor to.
What music did you deliver?
Well, there was a musical, and Johan, for instance, was singing, and I played the oboe, and we had a little band and several singers. But then Corona came, and we never actually
No more shows.
did the show.
Next time we explain you the physics of musical instruments, but that is going to take a little bit longer. Okay, now we are doing the thing. You are explaining for us. Yeah, indeed, victory indeed, beer mat victory. in a more university style like explanation, what's going on with the beer mats?
Yeah, welcome to my lecture on beer mats. So we have four nice images to illustrate this. The first is basically the configuration of this whole process. We have the beer mat here, basically a disc, and there's one force acting on it, namely gravity, which is pulling it down. And
this says air. It's written in a especially airy letter.
Yes, exactly. And also the beer mat is also its velocity into some forward direction, but together with the gravity, the velocity has a little downwards component, and the result of this is that the air is hitting the beer mat a little bit from below. And now comes in the aerodynamics. So the point of attack of this force, which is induced by the airstream, is not in the center of the disk, but has a little offset. So
this is the direction into which the beer mat is flying. So
yep.
Throwing direction, flying direction. Yeah.
Yes, exactly. And since this force is attacking the disk a little bit in the forward direction, it's lifting the disk up, so the disk would like to go upwards. But now comes in this the spinning of the disk, and this causes the disk not to flip upwards, but to do this rotation, this precession feature here. Shown in D, so it's not flipping like this, but it's going like this in the end. It would be easier if I had a beer mat to show this.
You do? Of course! There we go. Here are the beer mats. Oh, you can throw them by now.
Sure.
Jesus.
I can throw, I just can't.
Oh yeah, you can throw. Oh yeah, but not catch them. Okay, we'll see if he catches one. There we go! Beautifully done. That's physics, ladies and gentlemen. When you found out that the force is not like working in the very middle of the beer mat, but a little bit to the front, were you surprised, or being a physics professor, would you have expected it and you were just like, come on?
Well, it's not my field of research, so I actually didn't know it, but one could have had known it. So it's nothing really new.
It's knowable. You said you Googled a lot. Where do you Google such things?
At my computer usually.
No. No, but I mean, which search terms would you use?
Lift, airfoil, something like that. But I actually didn't really know what I was looking for originally, so it was quite tough to find this tiny piece of information that the aerodynamic center, that is the point of attack, is not in the center of mass.
Who's the person who found out? Do you know? Is it a famous person, or is it just somebody forgotten in time and space?
I don't know, actually.
Forgotten.
I mean, I looked into some strangely smelling old books, but no, I don't know any name attached to it.
Forgotten in time and space.
There is one name somewhere in my head. This whole phenomenon is condensed in some theorem. I think either Runge or Kutter, and then some mathematician, Jazubowski or something.
We will post it. We will post it under the video. We will post the link under the video. We are coming up with another idea concerning aerodynamics. Is it called aerodynamics in airplanes? Why do airplanes fly and how do airplanes fly? But our three guys here are not experts in airplanes. So we are thinking that this may probably have an application in airplane flying, but you look that up yourself, because we are here at the Helmholtz Institute in Bonn and not at an airspace facility. But probably two factors are of relevance. Number one, you have the little wings, not the winglets, that's something else, but the wings in the back to stabilize the flight. And the other one is that the airplane is pushed continuously. So these are two differences compared to our beer mat. But you look that up yourself. All right, we have further formulas here. And probably you can just lead us a little bit through those formulas to give us an idea of why you made the extra hassle to write down something apart from the very easily understandable explanations or very, very well understandable explanations that we saw on the other blackboard or green board.
Yeah, the original problem is that the formula of aerodynamics are quite complicated if you write them down completely in all of their beauty. You cannot solve them on paper, you can only solve them with a computer, and even then it's not sure that you really get the correct results. They're quite unstable. So we tried to find as simple formula as possible to still describe the beer mat pretty well. And what we came up with is this set of equations here, where we simply have the angle of the beer mat, which is this angle here.
Not the one.
Not that one. We simplified as far as we could by omitting all the things that are not necessary. So we describe this angle here, independence of how it is previously, and we describe the position of the beer mat, which is this x here, depending on gravity and the velocity of the beer mat. So the faster it goes, the more drag it has, the more it slows down. And obviously, if we have more gravity, then it falls down faster. And the important point here is that if it has some finite angle like this, it will not only fall downwards, but it will also accelerate sidewards. So it somehow slides through the air.
Learn a German word, abschmieren. Es schmiert ab.
Genau. Yeah, and this is what causes the beer mat to fly a curve in the end.
Then you have another formula a little bit further down. What is this? What is this beautiful letter here?
It's
It looks like a pet animal, like a cute Japanese pet animal.
yeah, it's a Greek letter theta, and this is precisely this angle here that we need to describe the trajectory of the beer mat.
How did former mathematicians and physicists calculate those formula of which you said that they can only be computed by computers? Did they do it by hand, or were they not known in former times? The complicated, long calculations.
I'm not an expert on this, but actually, as I understand it, they didn't really calculate. They usually just tried to put as realistic a wing or whatever into an air canal and then look what happened.
So they were just describing.
Nowadays, this is solved by large computers. So there are really big centers where they have computers which are only used to solve such aerodynamic equations.
Well, they're really complicated. You wanted to add something concerning the value of such research. So it's not just beer mat throwing as a self-purpose, but it has a different purpose.
Exactly. So what we actually try to do is that we came up with assumptions, and these assumptions were made such that we try to explain with these assumptions why we see how the beer mat behaves as it does. And these assumptions then lead to simplifications in these terribly complicated equations, which Johann just explained. And now we can use these simplified equations, which depend on our assumptions, of course, to make a prediction about the flight of a beer mat. And this we can then cross-check against our experimental effort that we did. And this is why it's so important that we did the experiment in the end. And then we found, okay, this matches. And this gives us confidence that our arguments or that our assumptions that we put in are actually correct and are actually really the cause of why the beer mat is flying.
And that is the very nature of natural sciences, that you really can predict something, and you're not just claiming to predict something which cannot be proven. So natural sciences are about proving and sometimes calculating things, but especially about predicting things. If you cannot predict something, it's probably not natural sciences. It's just an opinion or something. We are happy that you continue to listen and watch, because now we come to the final part of the interesting equation. And this... It's your handwriting, right?
Exactly.
Do you normally write readable and legible, or normally no?
No,
Or is it only
it's only important that I can read it.
Except formulas, they are written legibly. What does the final part of the formula describe?
Yeah, so this is now about the other direction. So far we had the forward direction, which we called x, and here it's the vector, but never mind. And then at some point we said that it starts to tilt, and then it turns to the left or to the right and makes a little curve. And this formula now describes what happens. So we have a first phase of the flight where it's just flying straight forward. And then when it starts to tilt, it starts this sidewards sliding. And this is actually described here. So we have below a certain timescale tau, which is characteristic for this system, we have no movement in the one direction, in this perpendicular direction. And then if the time becomes larger than this timescale, then we have this sliding to the sides, left or right.
And that is actually a beautiful thing. We have so much reality in such a little formula, right?
Indeed.
Indeed. What does that do to you? Like when you look at a formula like this, I mean, do you try to explain the beauty in this, or does nobody?
Oh, it's nice. It feels orderly to find order in the chaos.
Exactly. Okay, Ines. Now that we heard everything about beer mat throwing,
Yes.
you can try out several methods and we see if it works or not. What did you learn until now?
I must have spinning power in the
beer mat. That's a nice band name. Spinning power in the beer mat. Okay, let's go. Okay, one more. Aha, more stable. One more. Also astonishingly good. And you also did one where you just were flitching it a little bit.
Yeah. It's not a good method.
Very interesting. Are you surprised?
Yes. It's interesting.
You waited for it. Now it happens. The machine is going to get started. The BDSM machine, and we'll see what happens. I'm actually touching it. It feels good. Ines, you have an idea.
Yeah, rotate the machine
To a 90 degree angle. Of course, we're trying it out because these are, for now, experimental physicists. For now, for a minute. Yeah. Okay, people, the experiments did show that if you want to throw a beer mat predictably to a specific target, then don't let them turn around this way. That's the wrong way, right? But give them a spin into this direction and keep them up. Not this way, but this way. You got it? Maybe show it. Don't throw it, just show it. Okay, everybody is leaving. They're afraid. Okay, then give it a go. Well. This is all published now. I did a super brief radio show that brought us together. And what does your institute director say? What does the scientific international community say? How was this all understood?
Well, from the colleagues here at the university, we got a lot of positive feedback. They all found it cute and nice and interesting. And actually, when we submitted the paper, we got the referee report like 2 weeks later.
Yeah, astonishing.
And it was accepted without change.
Wow.
And this actually never happened to me. I have a number of papers now.
Wow, that is really cool. And it was not like medical people do it in the Lancet. This was not for an April 1st issue, but it is a regular, actual, scientific, nice, good, proper, peer-reviewed publication, right?
Yes, exactly.
Yeah. What did your relatives say when the paper came out?
They were, I got very, very nice comments. They were very happy about that.
Did they understand anything, or were they just like, you know?
Yes, they understood it, yeah.
Oh, really?
Yeah, my father's an engineer, so it's not hard to explain mechanics to him.
Oh, that's rewarding. That's good. What did your relatives say?
My relatives liked the movies very much, but they didn't read the paper, and I tried to explain them the physics background. They understood the basics, but actually they liked it.
Is it just that they like you and that you're a good person? Because sometimes that happens too.
Of course.
All of it.
Yeah.
You said you do a PhD, right? Did I understand that right?
Yeah.
Was it a PhD on the beer thing or on a different topic?
I actually wanted to include it, but in the end we decided to leave it out of my PhD thesis. So no, I'm doing my PhD on different topics. One might say more serious, others might say more boring, whatever.
What is the topic in simple terms?
So I'm doing condensed matter, and in particular I'm investigating electrical properties of a very thin material called graphene.
As thin as an indefinitely thin beer mat? Or thinner?
Even
Thinner.
thinner
Even thinner than an indefinitely thin beer mat.